Well, good morning, good afternoon, good evening to everyone, wherever you may be, somewhere across the world, hopefully somewhere nice. Thanks so much for joining us live here today for Serverless Office Hours, streaming on Twitch, Serverless Land YouTube, and also LinkedIn Live. My name is Julian Wood. I'm a developer advocate here within the Serverless team at AWS, and I'm joined today by Tom and Chris, and they're going to be talking about some cool stuff a little later. But let's just have a quick look at the previous week of Serverless and see what's been going on. Last week on Serverless Office Hours was a phenomenal episode. That's putting no pressure on Tom and Chris for this week. But yeah, when you got Alex DeBree talking DynamoDB and all the misconceptions he was bringing up, what a fantastic guest. You know, I wouldn't even say nuggets of information. This was gold bullion of information. So yeah, certainly please have a look at that. I can see the date is incorrect. That was last week. So sorry, apologies about that. But yeah, look on the Serverless Land YouTube channel, and Alex DeBree dropping a whole bunch of wisdom. In terms of what's new in AWS Serverless over the past few weeks, we spoke last week about Lambda. We're having some support for consumer IDs for MSK, so that's all Kafka. DynamoDB has got some bulk import support from Amazon S3 to new tables. But yeah, the big interesting one last week was AWS Step Functions. And this has got 14 new intrinsic functions, so you can process data more efficiently in workloads. And that basically means if you were using little mini Lambda functions to do some processing that you had with as one of the steps within your Step Function state machines, well, now you can just do this natively in Step Functions. And there are a whole bunch of sort of data wrangling things and also things like creating UUIDs and things like that. So yeah, just simplifies your Step Functions, makes them cheaper. Always good in my book. Some recent compute blog posts. Well, Benjamin Smith, as his usual Step Functions guru, has been cranking them out. So he's got a whole blog post introducing the new intrinsic functions and some nice workflows that he's been doing. As you regular watchers and listeners may know about our Serverless Espresso, where we show you how to build serverless applications using EventBridge and Step Functions and Lambda and DynamoDB. Well, Ben has showed how we could even make that application even simpler using these new intrinsic functions. And that goes hand in hand with his other post, building cost-effective Step Functions workflows. This is also about mixing and matching standard workflows and express workflows. Then on the next one, which came out about a week and a half ago, the world isn't melting, mixing up Kubernetes and AWS Lambda. Well, this is actually a really cool way for being able to deploy Lambda functions using the AWS controllers for Kubernetes. So if you are standardizing on the Kubernetes API, you can now do more things with AWS. The AWS Summit season is still on. Canberra and Australia was last week. And if you're Canadian or you're near Ottawa in Canada, certainly sign up and go and have a look at all the new and fun goodies that are going to be talked about at the AWS Summit. So this week, we are talking about AWS Lambda cost optimization. So happy to have Tom and Chris. Now, I'm in London, as many of you may know, and Tom and Chris are sort of at various points probably directly south from me. So there has been some thunder and lightning going on. My other colleague Ben Smith is on the coast at the end of the line. So we were talking earlier about maybe having to meet up on this sort of north-south axis. But yeah, welcome, Tom. First, what's your sort of journey coming into AWS, and what do you do with AWS?
Yeah, hi Julian, hi everyone on the stream. Yeah, Tom Moore, solution architect at AWS. Working with software vendors here in the UK. But also part of the serverless technical field community, so specializing in all things serverless. Yeah, as you say, kind of based just south of London, heading towards Brighton, and yeah, looks very stormy out the window, so hoping the power stays on for the duration of the stream today.
First world problems when working from home is
exactly,
power and things. Yeah, and Chris, tell us about yourself.
Hey everyone, so Chris, another solutions architect. On the same team as Tom, we work in the UK with some of the ISV customers, located also in the south of England. So again, hoping that we're not going to face any problems, although it doesn't look as bad on my end. Actually been a long-time AWS user. So before I joined AWS, actually been using AWS since about 2014. But recently found an urge to actually look at Lambda cost optimization, and some of the techniques we'll be covering today.
Awesome. Well, yeah, super important topic. That's one of the interesting things since joining AWS, how much we actually are focused on reducing cost for customers. Some other people aren't. So yeah, really great that you've written a whole bunch of stuff about this. Yeah, over to you. Where do you want to start with Lambda cost optimization?
Awesome. So yeah, sure. Let's just dive in. And I'd like to, wish everyone good morning, good afternoon, or good evening for wherever you are in the world. So we're going to walk through some of the techniques that can be beneficial today in optimizing your Lambda workloads. And I'd just like to also say that actually, even though we've got some material today, we've actually got a 2-part blog series that we'll be sharing at the end of this that actually covers more of the techniques in even greater depth.
Yeah, so we'll certainly, I'll also post links in the chat when you do get to that. Silly me, I didn't say, obviously this is Serverless Office Hours live, so please send us your questions or comments about this or other kind of topics, and hopefully we'll be able to inject them at various points in. So yeah, join the conversation. We'd love to hear from you.
Awesome. Okay. So let's begin. Now, before we do begin, we're just going to actually look at some specific guidance that actually we find is really well when we're optimizing our serverless applications. Just before we actually dive into those techniques, we'll look at what this guidance is. So, firstly, when we're developing applications, if we think of I guess a pre-serverless world, actually some of the ways in which we go about optimizing that is focusing on optimizing our code to improve that performance of running in production, and actually hopefully then seeing more efficient infrastructure usage. We might be thinking more, serving more web requests or consuming more events. But actually, in a serverless world, often we end up actually scaling our applications without always considering some of these limitations. But they have the same effect, right? So firstly, you build on usage. If we're taking Lambda, for example, in this case, you're going to be billed not only on the number of requests, but also the total duration and memory configuration. And so actually having efficient code helps to reduce the cost of running these applications whilst still providing an improvement in performance for your end users. It's not just about the function code itself. As applications move to a more decoupled world and take advantage of things like event-driven patterns, actually what you might have as a single-facing customer service actually could end up being many, many, many services behind the scenes. And so to actually optimize for cost, we really want those downstream applications to only be executed when they're required. And with those applications then focusing purely on the task at hand rather than identifying if it should be running, actually you're overall going to reduce the number of Lambda functions you should be invoking. Now, even when you've made those improvements that we're about to look at now, we want you to not just have it as a one-off exercise, but actually revisit it regularly. Sometimes as your application scales, new challenges can start to identify additional areas for improvement. And in the cloud, things don't just stay the same. We release new features and services pretty frequently. And so actually, to make the best use of your resources, you should actually make sure to review these so that you're actually having a constant cycle of providing more cost-efficient methods of running your applications. And then finally, when we're considering the methods that we're about to discuss, you do need to evaluate the trade-offs, both in terms of service and feature costs, but also actually the effort for your developers to implement these. And so if we take a non-essential Lambda function, for example, maybe it runs once or twice a month, actually versus a core Lambda function powering an API that's running thousands or tens of thousands or even hundreds of thousands of times a day, you want to prioritize the one that is going to have the maximum amount of savings. Now, before we do dive into those techniques, and don't worry, they're coming shortly, I just want to make sure we're all on the same page for Lambda pricing. Now, one of the most obvious components is actually going to be the function size, or actually probably more widely known as the memory configuration. Now, today, this company ranges on one end of the scale from 128 all the way up to 10 gigabytes of RAM. And as you continue to scale this, the vCPUs for that Lambda function also are going to increase up to a potential of 6 vCPUs. Now, if we also provide more memory and CPU, that function is ultimately going to hopefully perform faster, which is going to lower that total duration, which is great because our function's actually taking less time to execute. And if we're actually serving directly for our end users, that's giving them a faster response time, and that's great. But actually for cost savings, that's one of the elements, the duration of the function. So that is reducing the cost. Now, finally, you're also going to be billed on the total number of invocations that occur. Now, if we just go to the AWS Lambda pricing page, what we can actually see at the top is the prices that we have for each region. So we can just see them there. Now, I just want to point out before we scroll down this page, we've actually made a recent change to how Lambda billing is made. And so you'll actually notice now we have additional pricing tiers for customers. They're using larger amounts of Lambda each month. And if you're already using large amounts of Lambda, you don't need to make a change. That will be applied already.
Chris, can we just zoom in a little bit over there? I know it was just the pricing page, which I'll link to in the notes as well. But I mean, there are a lot of zeros over these numbers, which is quite one of the funny things with Lambda pricing, like 0.0, and you need a big calculator to work them out. But yeah, just so we can see. Thanks.
Sure. So that's one of the recent changes that we've made. I want to point out one that actually, for long-term Lambda users, they might not be so familiar with. So if we just scroll down to the memory configurations here, for anyone who's actually been using Lambda potentially since the start, or at least almost since the start, it was originally built in 100 millisecond blocks. And so actually, when it came to cost optimization, you might actually only try to cost optimize up to the nearest 100 milliseconds. You know, if it's 180, 190, there might have not been much effort required. But actually, I want to say back in reInvent 2020, we actually made a recent change to knock that down and now bill in 1 millisecond blocks. And so actually what this means with this more granular billing is that as you optimize your application, you're able to see those real-time savings. You're not having to push it past that 100 millisecond block anymore.
And many customers have been sort of shaving 70% off their bill. I think that was a quoted figure, some particularly fast run times with a sort of small requests. So yeah, that's a big impact.
Yeah, 100%. Now, what I really want to try and say is that over the next, we've got 48 minutes or so, we really want to keep the information about how Lambda is built at the top of our heads, because that's actually going to help us to make sense of some of the cost optimization techniques that we're going to have. Now, we're going to move on to the first of our techniques, but to start off, we're gonna play a quick game. Now, there's two Lambda functions.
Yeah, answers in the chat. Answers in the chat, please. A quiz, exciting.
Yes. So if you put your answers in the chat, we have two Lambda functions. We'll give you about 20, 30 seconds to say which one you prefer, or which one you think is cheaper, and then we'll actually give you the answer.
Well, I should have been more prepared with sort of some drum rolling or something to do the anticipation and everything.
Love to keep you on your feet, Julian.
Yeah, absolutely. I would sing, but I think that would just turn people off. It's probably not my forte.
Maybe we should put you on the spot, Julian, and ask you for the answer first.
Well, we can do that. We do have some votes coming in. Thank you, Aravin, joining us from YouTube, and also Steve joining us from YouTube as well. So Steve and Aravin both say 1 gig. Kunal also says 1 gig. Yeah. Ooh. So we have no dissenting voices at the moment. MJ Radicentia from AWS, from Twitch. Thank you for joining us. We have one which is correct so far. I'm not going to say which one. Zach Jones Noel joining us from Bengaluru in India. 1 gig running is cheaper. Yeah, we also
let's reveal the answer, I guess. So it is the one on the left, which is more expensive. So for some of you, that might not make much sense, but actually we're going to try and provide you the reason why that is now in our next section. So right sizing. Now, when we're thinking of the billing metrics that are used for the Lambda function, right sizing can actually be one of the first tools that we would use, and actually not just Lambda, but generally any application performance tuning. So by doing this, the idea is actually to reduce our cost without directly needing to change our code. And by going through that exercise, we're looking to run our workload at the lowest cost, really without having to compromise on any of the performance gains that we might have made. So to do this, we're going to need to understand what are the constraints of our application, and then to use this to identify the optimal requirements that would be used to keep our performance whilst lowering our cost. So actually today, we're going to be looking at a tool called the AWS Lambda Power Tuning tool. Hopefully some of you are familiar, but it might be new for some of you. Now this is going to enable us to find our Lambda's ideal memory configuration for that trade-off between cost and performance without us needing to guess it. So right now on our screen, we should be able to see the AWS Lambda Power Tuning tool GitHub page. Now, as I said, this provides a way to compare that cost and performance of our Lambda function against the number of memory configurations. So if we just scroll down, we should be able to actually see an idea of what this visualization looks like. So the idea is actually, by using that tool, you're able to visually see how your Lambda's cost and performance changes as that memory increases, which allows you to make a conscious decision on your Lambda, making sure that it's running at the most cost-efficient configuration, again, without compromising on that performance. And I just want to make sure that's clear. We're not trying to reduce our performance. We're trying to just make sure that we're running as cost-efficiently as possible. Now, there are a number of ways in which you can actually deploy it straight into your account. There's some links within the actual GitHub page that we've shared that will show you how to launch it. The way in which we're going to use, and probably the easiest, is using something called the Serverless Application Repository. So it's pretty simple. There's a deploy link at the top. We click on that deploy link. And then what will happen is we'll get to a second page where if we scroll down to the bottom, we could again click deploy. And within a couple of minutes, that's going to end up in our account. Now, we don't want to take a couple of minutes, so we actually deployed this ahead of time. But before we actually dive into that, let's look at the Lambda function that we're actually going to be tuning. Now, here we have it. We probably just need to zoom in a little bit. What we actually get with this Lambda function isn't too important. Just to give you a basic idea, it's running some basic math functions which are doing some computationally heavy tasks.
If we can do another zoom in or two, that would also be helpful for people like me who are a bit blind at the back.
Awesome. So if we just go to the test tab, we can give it a test. It should take about half a second through my previous testing, which, actually for a web request, if we scroll down, we can see, there we go, 553 milliseconds. So not too bad. We might think, hey, why would we want to improve that? And we can see it's used 95 meg of memory. And so actually that's quite close to that 128, which I mentioned at the beginning. That is the lowest possible memory configuration. But hey, I want to see actually, can I improve my performance and lower my cost more? So I'm going to try and run this through our step function for the Lambda power tuning tool.
Yeah, just if you didn't realize that the power tuner does actually deploy a step function state machine into your account, and it uses multiple parallel invocations with different memory allocations to give you a result. Super cool. Nicely done from Alex Castleboni, who used to be an AWS hero and now works with AWS. So yeah, we're lucky to have him. This is a super useful tool.
Awesome. So we'll just open up that step function state machine, and don't worry, we'll dive in a little bit deeper into what step functions are later in this. But we're going to actually start an execution, which is going to perform that tuning exercise for us. Again, the payload is available in the GitHub page that we're about to put in here, so don't worry, you don't need to try and copy it. It's in that GitHub page if you want to try it out for yourself. Now, we'll start the execution because it's going to take a little while. But if we just open up that execution input, I just want to talk about a couple of the things that are in here. So firstly, we're referencing what is the actual Lambda ARN that we're going to test against. Below that, we have our power values. And actually what these are the different memory configurations that we want to try against. So we start at 128, which is what we're currently at, all the way up to 2 gigabytes of RAM. Now we can see on the right, we've got some output. It's actually finished completing. Now, the one thing that we're probably going to get the most advantage from here is that visualization attribute. So if we copy that and then we open it up in a new tab, we should be able to see how our Lambda function is performing. And actually, it's pretty noticeable on the blue line, which is the total cost, that there is a bit of a dip as it goes throughout those memory configurations before it increases again. But I also want to bring your attention to that red line. In that red line, we can actually see the duration, which is the performance of that Lambda function, decreasing as we're increasing the memory configuration. And so actually, the best cost there, we get the recommendation, so you don't even need to do the math. The best cost is 512 megabytes. We've managed to cut our actual total performance time down by just short of 80%, and we've managed to make a saving of probably, my math isn't doing me any favors today, but probably about 15%, I'm guessing, from looking at that graph. But I recommend, if you do have any Lambda functions that you're running today that you think you might be able to run this exercise, to take a look at that tool and actually give it a go. See what your savings are. Yeah, great. So with that, I'm going to hand over to Tom to take us through the next of our tips.
Just quickly, some comments that came in. Will this run in parallel? And the answer is yes. So each of those memory configurations do run in parallel, and also you don't have to do 128, 256, 512, and do it up sort of linearly. Lambda functions work in 128 meg increments, so you could have 384 to your heart's content. And then also, Alex, thanks for joining us from YouTube. Is the state machine allowed to invoke all lambdas? Well, that's a permission thing that you do need to ensure you do have in your account. So it's not doing anything too magical. It is just basically creating multiple versions of your Lambda function with different, I wouldn't say versions, that's going to complicate it, multiple instances of your Lambda function, or even multiple copies of your Lambda function with different memory configurations, and then running them a certain number of times.
Cool. Yeah, and I've just shown on screen where that parallelization happens exactly. Cool. Yeah. So thanks, Chris. So on to the next session then, and we'll start this again with a small pop quiz. So which one of these costs more, both with the same memory configuration this time, but one taking 10 seconds and one taking 1 second? Hopefully this should be fairly obvious now based on everything we've gone through. Just give people a couple of seconds. But yeah, absolutely. The one that takes less time will save you some money and cost less, essentially, because we build on the duration that our function runs for. And this takes us nicely onto the next section, which is around code optimization. So the more optimal your code is, the faster it will run and the more money you'll save. And this will particularly become important to you as you start to scale out your Lambda functions, and they're invoking thousands of times a second. Particularly as we build per millisecond now, the more you can shave off that time in terms of code optimization, the faster your application is going to run, the better performance it's going to be, but the more money you're going to save. So how can we do this? We have lots of best practices around code optimization that you can find in the AWS documentation for Lambda, and in our blog post that we will link to later on. But actually, I'm going to show a technique using something called AWS X-Ray, which is a distributed tracing service that we have at AWS, which can help find bottlenecks in your application. And with Lambda, we can actually start to analyze where performance delays are inside of our code. So here on the screen, I've just got, I'm inside of a Cloud 9 environment, which is our cloud-based IDE we have at AWS, and I've just got a very simple serverless application model, or SAM template, set up here. And what this does is it creates a Lambda function, an API gateway fronting that Lambda function, and an SQS queue. And the idea is that you can post your order for a particular pizza topping, and the Lambda function will submit that particular order to an SQS queue. And now there are a couple of extra bits here as well. So we're using Systems Manager Parameter Store just to retrieve the name of the SQS queue to use. And further down here is where we've defined our function. Now, you don't have to necessarily worry too much about the CloudFormation or the SAM template. I'm just showing how this is set up. If we scroll down a little bit further here, we'll see that inside the properties of the serverless function, I've set tracing to active, and this essentially enables X-ray on the Lambda function. I've also added in here a Lambda layer, which is the easiest way to use the Lambda Power Tools for Python. So if you haven't heard of the Lambda Power Tools before, it's a series of open source tools which help do various different things inside a Lambda function, such as logging, handling parameters, caching, getting the best out of Lambda, really. And one of the tools it provides is an opinionated layer for tracing, so the ability to use X-ray, but in an easier way than using the SDK directly. So I'm using the power tools combined with enabling tracing to capture some performance data about this particular function. If I look inside the function code here, I've got some very simple Python code, and here's where I'm importing the Power Tools module, and inside of that I'm importing the tracing or the tracer utility. I'm instantiating an instance of tracer, and I've also decorated both my handler function and one of my subsequent functions inside of my code here. So this should then essentially give us some data inside of X-Ray. Now, I'm just going to make a quick post call to my API, and I'm ordering the topping of pepperoni. You can see that actually it responded fairly slowly, and that's deliberate for this demo. And the code has been set up to just return this particular OS environment variable, which will show us the X-Ray trace ID. So that invoke was successful. If I go over to the Lambda console, this is a function that was deployed as part of that SAM application. If I go to the monitor tab and onto traces, it will actually show me inside the Lambda console a snapshot of from X-Ray. Here we get a visual representation of what this particular function is doing. So you can see the Lambda function is calling out to a remote HTTP endpoint. It's calling out to Systems Manager Parameter Store and SQS as well. And if I scroll further down, then I'll see my individual traces for each invoke. And here the last one, which ran a few seconds ago. And if I go into that, it will open the X-Ray console. The X-Ray console is actually now part of the CloudWatch console. And here we'll get a little bit more detail as to what actually happened there. So again, here's the trace map, the service map, showing the full flow from the client through API gateway through to Lambda. But if I scroll down a bit further, I'm going to get this segments timeline. Now, this is where it's going to give me a breakdown of what exactly happened and the times or the duration for each part of that stage. So you can see here the API gateway part took 3.8 seconds. And API gateway invoked Lambda synchronously, so that's going to be the total time it took to respond to my particular curl request. Inside of that, the Lambda function took 3.84 seconds. So of that 3.86, you can see Lambda took the longest time to run there. That's exactly what we expect for this demo. So then drilling down a bit deeper, you can see, because I've added that Power Tools Lambda layer and I've imported the library, it's given me a greater breakdown inside the Lambda function. So I can see here the parameter store call took a total of 255 milliseconds. The call to an external HTTP endpoint took 60 milliseconds. And here's where the problem lies, actually. The sleepy function took a total of 2 seconds. So that's really where the delay is in my code. And from this information, I could then go back into my code and start to drill down to see where I can make some optimizations. In this case, it's a rather silly example, and I've got a sleep in here, which is rather pointless, and I can take that out. But you could see how you could then go through and start to pick parts of the code where you could focus your effort. Now, another part to mention is on that parameter retrieval, I'm essentially getting the name of the SQS queue from parameter store. And really the name of the queue is probably not going to change very often. So doing it inside the handler may not be the best place to retrieve that value, because essentially that's going to be retrieved on every single invoke. And if we go back to the X-Ray trace, you can see that's 255 milliseconds. Now, when we build per millisecond, that's quite a few milliseconds every single invoke, when actually that's really probably not necessary. So I could just move this line to outside the handler, and now that will only be run on initialization. So essentially a cold start when a Lambda execution environment is set up. So that's immediately going to save me some time in my function and save me some costs. Okay, great. Well, I think we're now back to Chris to talk through idle wait time.
Awesome. So I just wanted to quickly summarize, just for anyone who potentially has jumped in partway through. So the kind of techniques that we've actually looked at so far have actually been doing some right sizing, looking at how we optimize our code, but actually also looking at how Lambda is priced. And I mentioned it's based on duration, invocations, and that total memory configuration. As Tom just mentioned, we're going to now look at the avoiding of the idle wait time. So what we're actually talking about here is actually when you have potentially long gaps in your Lambda functions when they're waiting on another resource. For example, maybe you have a Lambda function. that invokes other Lambda functions, and it's just waiting for them to finish. Now, it's really important just thinking about how Lambda is built. You're paying by the millisecond just to actually wait on those Lambda functions. And so actually, to really get the best price from your Lambda, you need to avoid using it as an orchestrator. We would actually say that's an anti-pattern. The way in which I like to think of it is actually, if it has to wait, maybe ask yourself, is there a better way? Now, it's also important to really maximize the amount of time your application is spending on that processing time. We don't want to be waiting on just other resources that are just eating up on that price. And so AWS Step Functions is actually a service that offers orchestration as a service. It's more appropriate for that idle wait time. It already integrates with many AWS services natively, including Lambda, and it has built-in handlers to deal with error flows, to do retry logic, and also if you even need to wait a set period of time, it has that built into it. Now we're going to go into the console. Now what we can actually see here is a Lambda function that, let's just say it was built by a pizzeria. Someone's just launched a new pizzeria. Actually, they don't know too much about AWS, but they do know how to program. And so they thought, hey, Lambda does this. I don't have to manage the environment, so I'm going to develop it like this. If we just scroll down, what we'll actually see in the code is actually just these actions that we're basically invoking other Lambda functions. It's very simple. It is simply just calling another Lambda function and letting that do its thing. Now, it's probably not a great use of resource. And so actually, if we think about a pizzeria as well, there's other problems, right? I don't know about you, but Lambda functions, they have a maximum wait time of 15 minutes. I've never had a pizza arrive in 15 minutes from ordering. You also have to think about error handling and what happens if something goes wrong in the flow. How do you branch out and manage potentially really complex relationships? So this is part of what we're trying to resolve here. Now we're just going to give it a test just so we can actually see how that performs. Going to order 100 meat feast pizzas. Apparently, I'm very hungry. Don't worry. I feel free to come and grab one if you're ever in Brighton.
So we're just my address, please. That would be perfect if I could just. My kids would love 100 pizzas arriving at the door in under 15 minutes.
It'd be a great world. Now, obviously, we don't have 15 minutes to wait on the stream, so we have sped it up a little bit. But actually, what I want to just point out really is we've waited 15 minutes for this Lambda function to essentially just call other Lambda functions. And as I said, if it's, just being idle, there has to be a better way, and there is. So what we actually have is that step function service. Now, we've actually built a state machine you can see on the screen here, and here's its definition. So what we're actually getting out of this is actually a managed orchestration without potentially actually even having to change Lambda functions. In fact, actually, these Lambda functions are running the exact same code as that previous Lambda orchestrator. As long as they're accepting the same input and output between, it works. We're also getting a couple of additional advantages here. So actually, you'll notice that we have a bit of a branch that breaks out. So we're able to separate our actual pizza preparation and cooking from our notification of our customers. They're not, notification isn't a blocking task anymore. We've also been able to handle the errors there. So we've actually been able to break that out as separate error notifications. Now we're going to run this exact same test again using the exact input that we've gotten from the Lambda function event from before. And then we're just going to give it a test and see how does it perform. Now, whilst that's running, I just want to talk about the pricing model of step functions and how it's different to Lambda. So with step functions, with their standard workflows, they're going to be built on actual state transitions. So each of those hops that we saw, that's a state transition. Whereas Lambda is going to be built on the total duration. Now we can already see it's completed. Actually, that took less time than the Lambda orchestrator because we're now parallelizing things, which is great. And we're not having that idle wait time, which is, what we're trying to avoid here. We're only paying for what we're trying to do. Now, on top of that, we've actually gotten around another one of the things I spoke about earlier, which is with Lambdas, they have that maximum execution runtime of 15 minutes. For anyone who has longer running workflows, I'm talking, not minutes, but hours or days or even weeks. Step function standard workflows support up to 1 year with their workflow, with their individual workflows happening. And of course, we can run many in parallel of this. And so actually, that is an additional advantage that we're gaining here as well. So with that, we've talked a little bit about what step functions is. I'm now going to hand over to Tom to actually take us through the next of what our techniques is, which is going to build on even further what we've done with this step function.
Cool, thanks, Chris. So we'll start the next section again, keep the tradition going with a small pop quiz. Which one costs more, 128 megabyte seconds running for 1 second, or no function at all? No, of course, no function at all is going to save you some money there. So no, why am I saying this? Because actually there's something called direct integration that we can use with some of the serverless services, where we're just using Lambda essentially to proxy to another service using simple SDK calls. We can actually avoid using Lambda at all by going directly to that downstream service. So we're going to go back into the console, and we are going to go back to the example that Chris showed earlier, which was the pizzeria orchestrator workflow. And here I am actually in the step functions workflow studio. So if you haven't used this, this is an awesome tool to visually build and display your step functions workflows. And actually, one thing that's awesome about step functions is that we now support over 10,000 SDK integrations straight out of the box with step functions. And this has made it even easier with the Workflow Studio, because as you can see, there's pretty much every AWS service that you can think of down the left-hand side here. And underneath each of these are the relevant SDK calls for that particular service. So here for DynamoDB, we can create backups, we can delete items, we can describe tables, all the kind of typical SDK calls that you might do inside the Lambda function can actually be directly done inside the step function. So just to go through an example then, so in this particular workflow, it's all made up of Lambdas currently. Down the bottom here, we actually have an error handled situation. So if there's an error as part of the function, the workflow, it will take and invoke this error notification function. So if I go ahead and view that function and just take a look at what the code is doing. And inside this code, while this loads, we should be able to see that the code is actually very simple, and all it's doing is using the photo-free SDK for Python to contact the SNS SDK and publish a message. And the message that it publishes is just essentially a dump of the input event that comes to the Lambda function. So, it's fairly common for customers to have this kind of function, because things like step function didn't used to support the number of integrations that it does today. So worth going back and reviewing your code, as Chris said at the start, to make sure if there's any optimizations you can do. So back inside this step functions workflow, we're going to go and change that to essentially do the same SDK call that we're doing in Lambda, which is using publish. So I'll find SNS publish, can drag that into the workflow and Workflow Studio. And I'm actually going to just pass in here the same API parameters that I was doing inside Lambda. So passing in the message as the message body, essentially the entire input, and then setting the topic ARN to the pizza order error Lambda function. And then I can go ahead and just delete that particular Lambda function state. So now I'm only paying for the state transition, and I'm not paying for any Lambda costs there when the step functions workflow takes that particular route. So yeah, really, really great way to save some money, and encourage you to have a look at step functions because of this recent increase in the number of API actions that we support out of the box. Now, direct integration is not just limited to step functions. There's other places in the wider serverless ecosystem that we can do this. One of those is using API gateway. So sometimes people put Lambda functions behind API gateway to downstream send a message to SQS, for example, or write to a Kinesis delivery stream, a Firehose delivery stream. You can do certain direct integrations there to avoid the Lambda proxy in the middle. And actually, we go through one of those in the workshop we'll share later.
We do just have a question that's come in about how many state machines can you run concurrently? What is the max threshold? And I was just looking it up, but I didn't want to put you on the spot unless you more step functions guru than I am with some of these big numbers. But remember, standard workflows can run up to a year. So the maximum open executions per account. So these are the number of step functions, state machines that are currently running, is up to 1 million per region, and this can be increased to millions. So yeah, that's pretty high scale. For synchronous express workflows, concurrent executions is between 1,000 and 3,700, and that varies by regions. But that can also be increased to tens of thousands. So, yeah, you can run a lot of concurrent state machine invocations at the same time.
Yeah, thanks, Julian. I wouldn't have got that one off the top of my head.
The quizzes would start to get hard if we start looking at some of the
yeah, absolutely. Worth taking a look at these. And as I said, this is part of what Chris was saying at the start, where we need to continually go back and review our applications, because there's new features and new services coming out all the time that can help us save money. So what we might have implemented that was cost optimal a year ago might not be 1 year later. So always go back and iteratively improve your applications. I'm going to hand back now to Chris to talk to us about logging.
Thanks, Tom. So I guess just a recap of where we're actually at. We've actually talked a lot about application changes that we can make to our Lambda functions. That's our right sizing, code tuning. We did avoiding the idle wait time with step functions, and now Tom's just taken us through direct integrations. But we're now going to actually look more at the operational changes that we can make to lower our costs, starting with logging. Now, for anyone who's actually been using Lambda functions for a little while, you're probably familiar with the fact that actually for the logs, they're going to end up being shipped into CloudWatch logs. That logging is going to include all of the output from your function. That's any code that you didn't even mean to make, and it's just printing out, or potential just debug. That's going to make its way out with that Lambda output. And so actually, by assessing what you're already logging today, you should be able to start reducing that total cost of that data collection within CloudWatch logs, log groups, and that ingestion into CloudWatch logs. That's one part of that pricing. Now, we've already touched just a second ago on one of those easiest wins, which is going to be debug logs in production, right? Now, I know I've been a developer before. It can be quite easy as code progresses from development into production to actually accidentally print a load of debug. But actually, by starting to disable that, potentially use environment variables to control what is logged in, which environment, you can have a pretty tangible effect on your CloudWatch logs, log pricing. Now, also, as developers, we should really be focusing on creating a more consistent format for our logs. So I'm on about, defining a more strict structure. Perhaps you create a function that is going to take in parameter variables and then, print that into a JSON format. What we're doing here is actually really trying to remove the ability to just generate loads and loads of bloated strings that are quite easy, or quite hard rather, to use in a investigation. And so we can also then take advantage of additional CloudWatch logs features, things like deriving patterns from your logs and then being able to create alarms based on those metric patterns. But also, the other thing that you want to consider is actually whether or not those logs are actually adding any value at all to your investigation. Sometimes we just like to put things in and it's not really going to help. It's just going to create more white noise. Now, the final thing for log ingestion that we want to think about is whether or not it's the appropriate storage medium for us to actually be publishing to. So an example here, if you're trying to publish to long-term analytics platforms, actually CloudWatch logs isn't going to be that, that recommended solution. You'd be more looking for something like Amazon S3. Or again, maybe you're looking to just understand a little bit more about the function runtimes. And we've already covered a service here that does that, X-Ray. And so actually, even if you're already using it today, or maybe you're not using it, you can start to move that into X-Ray, including any of that metadata that you might have been printing out. I mentioned actually log ingestion, that's just one part of the pricing elements. And so if we go into the console, we're going to cover the storage elements of CloudWatch pricing as well. Now, sometimes actually when you're publishing, you might not actually realize that the logs are just being retained forever and ever and ever. But they are going to be, and that's going to ultimately lead to storage costs down the line. Now, sometimes it can also be really difficult to understand, when should I actually get rid of these logs? But I think probably the way in which I like to think about it is actually to think, is this log going to add value in real time? Like, am I going to get real usage out of being able to access this log immediately? If the answer is, a certain length of time, actually we can take advantage of retention periods. So here, if we click on one of our logs of our Lambda functions, we can actually set a period after which CloudWatch Logs is automatically going to retire those logs for us. No, we're not having to manually depreciate them. They're going to be handled for us. Now, that's great, but actually sometimes customers need to be able to keep these logs for a lengthier period, but they don't need immediate access. And so actually we do have the ability to export them to a service such as Amazon S3. What this is going to enable us to do is to keep those logs in a cheaper storage medium, and then take advantage of features like lifecycle rules within Amazon S3 to gradually transition and move them into an archive storage format, something like in Glacier Deep Archive, where we can then actually have them available, but we might not need them immediately available, and still keep those costs as low as possible. So if you can wait, potentially hours or days, actually you can transition and then still keep that cost as low as possible. Now, with that, I'm going to hand over back to Tom Moore to take us through the last of our tips.
Cool, thanks, Chris. Yeah, in the last few minutes that we have left, then I just want to talk about pricing models. So a lot of the stuff that we've talked about up until now has been around code changes, architecture changes. But I just want to cover in the last few minutes some stuff on pricing for Lambda. So one option that we have to actually save some money with Lambda without making any changes to code or architecture is to use something called compute savings plans. Now, you may be familiar with savings plans or reserved instances in reference to EC2 instances, but actually compute savings plans can also apply to AWS Lambda. So they work in the same way in that in return for some commitment to some consistent usage measured in dollars per hour for a particular 1 or 3 year term, you in exchange get a discount on your Lambda functions. So if I scroll down a little bit, you can see here we've got the compute savings plans for AWS Lambda. You can select a particular term, choose to pay upfront, partially upfront, or not upfront at all. And down the bottom here, it will actually show you the savings that you'll make over on demand. So there's no saving in terms of the number of requests, but there is a saving on that per gigabyte per second charge, so essentially the duration charge. So this is just a billing mechanism. As I say, don't make any changes to the code. If you have consistent Lambda usage, then worth looking at compute savings plans. And if you are using other services such as Amazon EC2 or AWS Fargate, which is the serverless container service, then these will automatically apply to those and give you a discount as well. Now, if I scroll back down to the table at the bottom, you'll see here that there's some other items in this table, and one of them is this thing here, AWS Lambda duration dash ARM. Now, what does this mean? Something that we haven't mentioned yet is that Lambda supports Graviton 2 as a different architecture type. So Graviton 2 is AWS's own ARM-based CPUs that we have available for various other services, including EC2, but it's also available for Lambda. So if we go back over to the original billing page that Chris was showing straight at the start of the session, there's actually 2 tabs for the memory pricing here for the duration. One is for x86, which was the original default, but we now have the option for ARM-based pricing, and this is typically 20% lower than the x86 pricing. And actually, because these are ARM-based CPUs, they can give you up to 19% better performance. Now, whether you can use ARM or Graviton 2 Lambda functions depends on the code that you have. It's typically an easier transition if you're using some an interpreted language like Python or Node, because AWS will provide the managed runtime with the compiled binaries for Python for that already. And you're probably going to make very minimal changes to your code, if any. But what you do need to watch out for is the dependencies that you use, and you may need to switch those to use ones that are compatible with ARM. So how do you do this? How do you make this change inside your Lambda function? So we'll just go over to one example from earlier. This is in the Lambda console. Down the bottom here, in the runtime settings, you can actually see the architecture of this is currently set to x86. So all we need to do is go and edit that and select ARM. And that's it. The next time the function is invoked, it will use Graviton 2 CPUs and potentially see a cost saving on the per millisecond billing, but also the function may perform better and also reduce the time there as well. So always recommend that you test these functions when making the change to make sure your code works, because it is an architecture change in the CPU you're using behind the scenes. But also run it through the power tuning tool that we showed earlier. So you can do a comparison. You can do the different memory profiles that Chris showed earlier for x86, then do it again for Graviton 2, and actually find the sweet spot to see whether Graviton's saving you money. Hopefully it is, and then you can make that decision on whether you make the change or not.
And with power tuning, that's actually going to show you it in the same graph. So the 2 lines we saw before, it's actually going to be 4 lines for each architecture pattern, and you can very clearly see whether you're going to save some money.
Yeah, I'm not sure if we have an example of that. Yeah, but I think it may be in the blog post.
It's in the blog.
As Julian said, you can see the 2 lines in the same graph to make it really easy to compare. Okay, so that pretty much brings us to a close today. Are there any other questions, Julian, on the chat?
Yeah, there certainly will do. I'm just going to grab some too. I'm just doing the Graviton on Lambda. I'm just posting that link that you've been provided over there. Yeah, I mean, this is sort of super interesting. I will also post those blog posts as well. Of course, we've got always some keen listeners who've got some of their own suggestions for reducing your Lambda costs. And I know one of your suggestions was having no Lambda function at all. But what if a Lambda function doesn't even invoke? So our good friend Kirk was talking about Lambda event filtering for cost savings. So if you aren't aware from this, if you're using things like Kinesis and MSK and DynamoDB, the event source mapping, this is the polar that Lambda runs on your behalf, does the event filtering there and then. And if it doesn't match the event, that is literally going to not invoke your Lambda function. So Zach Jones-Noel has saved a lot of money already, significantly. So yeah, that's also another winner. I think just having a quick look through, we've got loads of great comments, lots of answers about all the different memory indications. There was some information about sort of when we're talking about power tuner and who around. Thanks for joining us. What if my Lambda uses the same S3 location and I'm not allowed to run them in parallel, as that might mess up my data? Yes, that sort of is a concern, but when you're doing this Lambda power tuning, you're not really using it as an event trigger. So normally you would place something in S3 and that's going to trigger a particular Lambda function. What you would probably do in this scenario, and Chris and Tom jump in if you have some more to add, you would probably sort of create a test Lambda function for this, and this would maybe manually pull that S3 data, that object down from S3 and then iterate from the direct trigger.
I'm not sure if it's the same for everyone, but your audio is cutting out a little bit, Julian. Yeah, so one other thing I was going to show, we talked about the power tuning, the power tools throughout today. So if you haven't used these before, they're available for Python, TypeScript, and now .NET as well. The tracer tool was one that I used earlier, but there are some really there's some other useful core utilities that are part of this. One of them is a logger. So Chris was talking about making sure we save money on logs. So on the topic of logging and storing that in a useful and cost-effective manner, using the logger utility, we can actually pass in a particular logging level. So setting as an environment variable the particular logging level, whether we're going to write out info, debug, error logs, and then we can easily change that by tweaking this environment variable on the function as to whether the function is actually running in debug mode and we want to output a lot more data to CloudWatch, or whether we want to tune that right back just to get the bare bones when we're in production. There are other things in here as well. So I talked about parameters and retrieving parameters from parameter store. The parameter utility will help with caching that value in memory. So again, we're not making SDK calls to parameter store when we've already got it held in memory. Again, saving us some time and duration, and reducing the number of calls to parameter store as well. Yeah, I still can't hear you, Julian, unfortunately.
I can hear the rain.
Yeah, one thing, so we've got the links to the blog post there, and there's also the hands-on workshop, which we're linked to in the chat. There's a couple other things mentioned there, like event filtering. We've actually covered this in the blog post and in the workshop, but we didn't have time to go through it today. As mentioned, it's a really great way to save by not invoking the Lambda function from things like DynamoDB streams or SQS. But we're also covered in here as well things about asynchronous workflows, as well as provision concurrency, which we also haven't talked about today. So actually, provision concurrency can help to reduce the cold start invocation time and actually save some money in certain conditions over the standard model.
Nothing's done. Is my audio any better?
Yeah, I can hear it slightly now.
Who knows? Gremlins in the system. I am posting the links to your amazing blog posts with even some more information. So yeah, hopefully that will at least give you some more starting and jumping off points that you can do. And also there is a really good workshop that Tom and Chris mentioned, and that's also super useful to be able to put some of this into action. And there was a question earlier about some of the code is available for that workshop. You'll be able to look at some of the code to see how some of this things work. Well, Tom, Chris, I really want to thank you for your time. I love this extensive walkthrough of a whole number of things. There's
So Julian, unfortunately, is cut out again there. But yeah, thank you very much, everyone, for listening today. Hopefully it was a useful session. The links are in the chat, but otherwise we'll see you next time on Serverless Office Hours.
Thanks, everyone.
Thanks all. Have a good day. Bye.
Bye.